We're also going to talk a lot about light in this class. And so you need to be familiar with the various ways of describing the different kinds of light that are found. So a light ray consists of waves that we'll talk more about in future lectures, but one way to characterize the different kinds of light waves is by the wavelength, which is the distance between two adjacent peaks. It's given the Greek letter lambda to describe the wavelength, and the units of wavelength are the number of cycles per centimeter. I have this upside down here. No, centimeters per cycle. That's centimeters per cycle. And a lot of times the units of cycle are left out, sort of implicit. And so sometimes, very often, you will see wavelength described in units of centimeters. Another way to describe light is in terms of the frequency of light. So light is moving at some speed, c, the speed of light. And so if you're just sitting here watching this light go past you, you can count the peaks as they're coming. And so the frequency of the light, which is given the Greek letter nu, has units of cycles per second. Or since they tend to drop the cycles, you can see this written as just 1/seconds, or seconds to the -1. A little confusing if you don't know what's going on, but it's not that hard. So if we want to get some more factor label practice at converting units, this is a good example. Let's say we have a wavelength of light and we want to calculate its frequency. So the frequency has units of cycles per second, so that's what we want. And looking at the wavelength, the wavelength itself is centimeters per cycle, but looks like we want the cycles to be on top. So I'm going to put the wavelength upside down, 1/lambda. And so that gives us units here of cycles per centimeter, the inverse of lambda there. And then the speed of light, c, can be used to cancel the centimeters and get us the cycles per second that we're looking for. Another metric of light that turns out to be useful when we start talking about infrared light is called the wave number. And the wave number is simply the number of waves within 1 centimeter of distance. So you count the number of peaks in there, and the units of that are cycles per centimeter, or by ignoring the cycles there, it's oftentimes written as 1/centimeters, or centimeters raised to the power of -1. And so the wave number is just given the regular letter n. So if the best insulating windows would be ones that had nothing in between the two panes of glass, just a vacuum, think about the Earth and the Sun, which are separated from each other by 93 million miles of vacuum. So it's kind of amazing, actually, that the lump of atoms here that is the Earth, the kinetic energy of those atoms has anything to do with the energy of the atoms in the Sun or anything else in space. It turns out that the way energy can be transferred through a vacuum is by means of light. So light is composed of two properties of space-time. One of them is the electric field, and the other is the magnetic field. So the electric field is manifested in that if you take something that has a positive charge, like a proton, an H+ atom, like what changes the acidity of water, that has a positive charge, and then an electron is a particle that has a negative charge, and you sort of set those things close to each other, they will feel each other's presence. They will want to come together, even though there's nothing in between them but vacuum. So the electric field is what these things are feeling, and that is sort of a property of the vacuum, a property of space. Another property is the magnetic field, and so I've drawn two magnets with north and south poles, and so the south pole of one magnet will be attracted to the north pole of another. And there are some differences here. One is that in the magnetic field, there's no such thing as a magnetic monopole, something that only has a north or a south charge. Electrical fields, you do have electric monopoles, an electron or the proton. But in the magnetic field, you just sort of have things where the charges are separated from each other like this. Another difference is that the magnetic field can reach farther. If you have two magnets and they're pretty strong, you can hold them pretty far apart and you'll feel them pulling together. Whereas if you take a car battery and a jumper cable, do not try this at home, but if you did, hook the one part of the jumper cable to the plus and then the other part of the same wire, took it close to the minus, if you actually touched it, it would be an explosion. But before you touch it, you don't feel much attraction because it doesn't make it as far in space as the magnetic field does. So the two fields are coupled together by the fact that if you change the electric field, if you oscillate it, move it up and down, dial it up and down, it will induce a magnetic field. And so this is how, for example, an electromagnet works, or an electric motor uses this technique. Or if you change the magnetic field, that can induce an electric field. And that's how, for example, a generator works. So if you have some power from a waterfall or something and you're twisting some magnets around, you can use that to generate electricity. So light is a coupled oscillation of the electric and the magnetic fields. So it's like the energy bounces back and forth between the electric to the magnetic and back again. So if you were to draw a graph of the electric field as a function of time or distance, either way, since it's sort of a wave, this is a time where the electric field is changing. And as a result, this induces a strong magnetic field. Now here, the magnetic field is collapsing and changing, and so that induces a strong electric field. And so the energy is sort of bouncing back and forth between the electric and the magnetic fields. Now, this thing sets up a wave that's very analogous to a water wave on the surface of water. If this is a flat surface of the water and you make the water actually do like this, there's gravity tending to pull this water down and tending to push that water up and make it sort of go back to a flat surface. But if you do it just right, there can be motion of the water in the wave in a sort of circular pattern like this that creates another wave a few seconds later that has the same shape as the first wave. And the point is, the only way this can work is if the speed of the wave is right, so that it can sort of self-reproduce itself like this, make something that looks like it did, only just moved over a little bit in space. So if you tried to make a water wave and make it go 100 miles an hour, it would break. It wouldn't work. It wouldn't self-replicate, and so it wouldn't be a wave. Well, light is the same way. It has to reproduce itself. It has to bounce the energy from the electric field to the magnetic field and back again so that it looks the same way after a split second, but just moved in space. And that's what sets up the speed of light, is this requirement that it sort of ring like a bell, so that it reproduces itself. The way that electromagnetic radiation or light exchanges energy with objects is mostly through the electric field. So what happens is the electric field of the light that's coming in acts on a charged oscillator of the object that we're talking about. And if the frequency, there's a Greek letter nu, the frequency of the light is pretty much the same as the frequency of this oscillator, then the energy from this light being carried through the vacuum can be dumped into this oscillator. And you can heat the thing up through the vacuum. So we're going to talk about the light that comes off of an object, because this is a two-way street. If the light can come in and be absorbed by this oscillating piece of matter. If you have this matter being oscillated just because it's warm, it can also create light and send it back out. And so we're going to talk about the kinds of light that this object emits by thinking about a spectrum, which is a plot of how bright the light is as a function of the different frequencies or wavelengths or colors or however you want to describe the different kinds of light. So it's a plot that looks kind of like this. It's got an intensity on the vertical axis, and then we're going to use wave numbers on the horizontal axis as our index of colors. So the units on the intensity axis are watts per square meter per wave number. And the reason why that's done is because that way, if you have a range of light color, say between 1 and 2 wave number units, 1 and 2 waves per centimeter, for example, then the area under this curve is going to be equal to watts per meter squared per n times n, and the n's will cancel, leaving us just with a total of watts per square meter. So that means that these plots are drawn so that the area under the total curve is the total energy leaving the object in nice units that you now understand of watts per square meter of the surface of the object. So what those spectra look like are these sort of humps. I've drawn 3 of these different humps. This one's sort of off the top of the chalkboard there, because you get different curves depending on how warm the object is. So as the object gets warmer, the peak energy, which is where the intensity is the strongest, shifts in this direction toward shorter wavelength or higher wave number, more energetic light. So you probably have known this before by thinking about sort of red hot and white hot. So an object that's just at room temperature is shining light, but it's all in the infrared, so we can't see it with our eyes that can only see in the visible range. But as the object gets hotter and hotter, the tail starts to encroach in the visible range, and you start to see some red color there. And then if it gets really hot, it can fill up the whole visible range, and that's when something gets white hot. So white hot is much hotter than red hot. You already sort of knew that, right? The other thing about this spectrum is that it gets much bigger as you get hotter. And it turns out that there's a formula describing this. It's right here. The total energy in watts per square meter is given by these 3 terms. The first is epsilon, which I'll explain next. The second is the Stefan-Boltzmann constant, which is just a constant number you can look up in a book. It never changes. And then the third is the temperature in kelvins raised to the 4th power. So you raise it to the 4th power, that means if you double the temperature, the energy flux goes up by a factor of 2 to the 4th, which is 16. So it's a very, very powerful function of temperature. So back to this term now, epsilon. This relates to a quantity, whether the object is what they call a black body or not. So if an object is a black body, it's as though it's a musical instrument that has all of the notes. So like a piano that has all the keys, if you just hit it with a big hammer or something, make all of the keys vibrate at once, you'll get this big wall of sound like this. But if you have a piano that's missing a bunch of strings in the middle and you do the same thing, you'll get some low notes and you'll get some high notes, but there will be some missing stuff in the middle. So this is what a physicist would call a black body, because it makes a smooth black body curve like this, and the epsilon value for this would be 1. So you'd put in a number 1 here, and there's no units to epsilon. It either goes for 0 if an object had no of these oscillators and couldn't make any infrared light at all, to 1 if it had all of the notes and could make all the different frequencies.